Today we're going to start Chapter 8. Chapter 8 is about finding the inverse of exponential functions. Back in Chapter 7, the chapter that we just left, we talked about exponential functions. So what we're going to do in this chapter is we're going to take these exponential functions, we're going to find the inverse of them, and there's a special name for the inverse of exponential functions, and we'll see that in just a couple minutes. Down here you have a graph. And this is a graph of y equals 2 to the x. And if you wanted to put y equals 2 to the x in your calculator, y equals 2 to the x, press the graph button, and it looks like this. The table of values shows you what you could, specific points you could put on that graph. But I've graphed this for you. This is y equals 2 to the x. You should have an arrow on the end, an arrow on this end, and there's an asymptote of this y equals 2 to the x, and that asymptote is the x-axis, which has an equation y equals 0. So here's y equals 2 to the x. Is nothing new. We graphed it last chapter. What we're going to do with this chapter is we're going to take this graph, we're going to find the inverse of it. And to find the inverse of anything, it's a reflection over the line y equals x. So I drew in a dotted line here. This line, you can put arrows on the end of the dotted line. This dotted line is y equals x. So reflect this curve over top of the line y equals x, and you're going to get a different graph, a different function altogether that we're going to look at in a couple minutes. So this next bullet said when we reflect over the line y equals x, we switch x and y. That's how you find the inverse of any function, is you switch x and y. So the equation of the reflection of y equals 2 to the x is switch x and y, and you get x is equal to 2 to the power of y. So reflected over this line y equals x, we're going to graph the function x equals 2 to the y. But we usually don't write a function unless it's solved for y. Now we want to rewrite x equals 2 to the y that is solved for y. Well, if you take a look at this equation, x equals 2 to the y, if you want to get y by itself, there's no way in algebra you know how to get y by itself when the function looks like this exponentially. You can't divide both sides by 2 because this doesn't say x equals 2 times y. If it said 2 times y, then yes, we divide both sides by 2, but this is 2 to the power of y. So if we want to solve this equation for y, get y by itself when this little y is an exponent, the only way to do that is to invent a new function, and this new function is called a logarithm. A logarithm is an exponent, and I'm probably going to ask you this 100 times during this chapter, just like I asked you what the value of I was equal to in one of the previous chapters. I'm going to ask you, what is a logarithm? And you're going to tell me a logarithm is an exponent. And I'll say, what's a logarithm? And you'll say, a logarithm is an exponent. And I'll say it 100 times. And finally, you will remember that a logarithm is an exponent. This y up here is an exponent. So x equals 2 to the y. If you want to solve it for y, y is an exponent. Well, the exponent we call a logarithm. And a logarithm is abbreviated with just the first 3 letters, log. Y equals log of x. And that's it. If you want to solve x equals 2 to the y for y, you get y equals log of x. They are the same thing. Right down here, here's another very important point on this piece of paper. That's what I said up here. X equals 2 to the y is the exact same thing if you want to solve it for y as y is equal to log. Oh, I forgot the little base up here. So what you want to do is you want to insert a little 2 as a subscript. All right, the 2 is lower than that x. So it's very important that you put a little 2 because that tells you what the base is of this exponential equation. We're going to look at logarithms with other bases. So if you want to reflect this y equals 2 to the x across the line y equals x by switching all the x's and y's, you can start with this point here, 0, 1. 0, 1 reflected in the line y equals x becomes 1, 0. This next point is 1, 2. 1, 2 becomes 2, 1. The next point here is 2, 4. Well, 2, 4 becomes 4, 2. The next point is 3, 8, and 3, 8 becomes 8, 3. The next point on this graph is 4, 16. It looks like that's the last one we can see. And 4, 16 becomes a reflected 16, 4. The other points to the left of the y-axis is negative 1, a half. So you go over a half, negative 1. The next point is negative 2, comma, a quarter. So you go over a quarter and down 2. So we're going to connect all these points with a nice smooth curve, put an arrow on the end, put an arrow on the end. Now this time we have an asymptote of the y-axis, which has an equation x equals 0 is the asymptote of what we just graphed, y is equal to the log, with a little 2 down here, of x. Let's write this, y equals log, with a little 2 down here, of x. That means base 2. So here we go, the inverse of, remember f of x is the same thing as y, so the inverse of y equals 2 to the x, you don't say x equals 2 to the y, you say y is equal to the log, base 2 of x. And the inverse of y equals 3 to the x is y is equal to the log base 3 of x. See this base? Becomes this little subscript of a 3. They're inverses of each other if you switch x and y and solve for y. Here, y equals 5 to the x. If you want to switch x and y, solve for y, you get y is equal to the log. And this time the base is 5, so you put a little subscript of 5 of x. And here's some other log graphs. Log graphs all have the same shape, kind of shaped like a square root graph almost. But we'll just take a look at 3 of these log graphs. They all have different bases. This top one here is y is equal to the log base 2 of x. This one down here is y is equal to the log base 3 of x because it goes through the point 3, 1. This went through the point 2, 1, so it's log base 2 of x. This graph right here goes through the point 5, 1, so this is y equals log base 5 of x. So these 3 graphs are these 3 equations up here that we just wrote down. What's the domain of a log graph? What could the x's possibly be? Well, since there's an asymptote of the y-axis, or x equals 0 is the asymptote, you should probably write this down again and again so you don't forget it. X equals 0 is the asymptote, so that means that these graphs get really close to the y-axis, but they never will touch it. So the domain of the log graph is x has got to be greater than 0. Range is lowest to highest. Well, there's no lowest, there's no highest, so the range is all real numbers. And the equation of that asymptote is x equals 0, and that is the y-axis. So you always want to make that dotted. Make sure asymptotes are dotted when you graph them. And you can see here this base goes from 2 to 3 to 5, and it says the larger the base, what happens to these graphs? The larger the base, the closer these graphs get to the x-axis. So if you can imagine, there could be a log base 10 of x or a log base 20 of x. The bigger the base, the closer they get to the x-axis, but they'll never go down here. They're always going to stay above the x-axis as they go out this way. Over here, I'm going to show you that these equations that we studied in the last chapter, like 2 cubed equals 8, can be written in log form. These are the exact same thing, just written 2 different ways. 2 to the third equals 8 is the same thing as log, which means an exponent. Remember, what is a logarithm? You're going to say a logarithm is an exponent. Well, this says the exponent on the base 2 is 3, and that's going to give you an 8. So it's kind of a backwards thinking. You start here with the 2, the base 2. Since a log is an exponent, what this is really saying is 2 raised up to the third power is equal to 8. But they're the same thing written two different ways. One's called exponential form, the other's called logarithmic form. Over here, we learned last chapter that 2 to the 5th is 32. Well, if I wanted to write this same thing in log form, the exponent, which is a log, on the base 2, 2 to the 5th power is equal to 32. So just the same equation written two different ways that you have to recognize. So what we're going to do is we're going to take these 6 exponential equations and we're going to rewrite them in log form. And when you get to class tomorrow, you're going to get practice on this. So here we go. In log form, we start out with the word log. This time the base is 5. And then the 625 goes next. And a log is an exponent. Right? See that exponent? Or if you wanted to write it this way, 4 is equal to the log base 5 of 625. Either way is fine with me, and they're both correct. Either. All right. Sometimes I like to write it this way because I say to myself, 4 is the exponent on 5. That's going to equal 625. For example, number 2, I might say, well, 3 is the exponent, because a log is an exponent. 3 is the exponent on base 6. That's going to be equal to 216. 1/3 is the exponent on little base 27. That's going to be equal to 1/3. And what this is saying, if you think about it in the other way, you're going to say 27 to the 1/3 power is equal to 3. Sorry. My mistake. Fix it. Sorry. 27 to the 1/3 power is equal to 3. Good thing I checked my answer. On number 4, negative 1/4 is the exponent. On what base? On base 16. That's going to give us a half. Or in other words, 16 to the negative 1/4 power is equal to a half. Number 5, negative 2 is the exponent. On what base? On base 7. That's going to give us 1/49. Or in other words, 7 to the negative 2 is equal to 1/49. And then this last example here, 3, see the 3 up here? 3 is the exponent. On base a half, that's going to give us an 1/8. Or in other words, 1/2 to the 3rd power is equal to an 1/8. Now what we have down here in the next 6 examples is we have a log equation, and we're going to rewrite it in exponential form, so we're going to go the other way around. So what this is saying is the exponent on the base 6. So we're going to, sometimes I rewrite this, I say 2 equals log base 6 of 36. I just switch the sides of the equation because sometimes that helps me say 2 is the exponent on 6 that is equal to 36. So we can say this is the same thing as 6 squared equals 36. This next one is the same thing as saying 9 to the 3rd power is equal to 729. Same thing, different forms. This one says 3 to the negative 4th power, is equal to 1/81. And is it true? We can always check. Let's see. 3 to the power of negative 4, and I'm going to math frac. 3 to the negative 4 power is 1/81. So that's a true statement mathematically. Number 10, sometimes I'll rewrite it. 1/2 equals log base 144 of 12. So in other words, we can write this exponentially as 144 to the 1/2 power is equal to 12. And hopefully you remember from the last chapter, the 1/2 power means the square root. So in other words, the square root of 124 is 12. That's true. This one, number 11, says 4 raised up to the third power is equal to 64. Sometimes we call this rolling the log. You start down here and you roll the log over this way. That's another way to remember how to rewrite them. And number 12 says 10 to the power of negative 3 is equal to 0.001. And then to finish this up, finish this page, log base 7 of x is equal to 2. Oh dear, now we have to solve for x. Well, sometimes I rewrite this as 2 equals log base 7 of x. So 2 is the exponent on 7 that gives you x. In other words, 7 squared equals x. Or in other words, 49 is equal to x. We've just solved that for x. All right? This hint says write in exponential form first is what we did. This one says 4 to the power of n is equal to 64. Well, 4 is as low, well, 4 is not quite as low as it can get exponentially, but we can write 64 as 4 to the third. And when we have the bases that are the same, we can ignore them and we just say n is equal to 3. We make those exponents equal to each other. And number 15 says the base is b, the exponent is a half, and it's equal to 9. So how do we get rid of an exponent? That's a fraction. We raise both sides to the power of the reciprocal. 1/2, the reciprocal of 1/2 is 2 over 1, which is just 2. Whoops, 2 over 1. So b is equal to 9 to the 2 second power. 9 to the second power is 81. And that's it. And that's your introduction to Chapter 8, Logarithmic Functions.